Hello everyone and welcome back to the NPTEL course in Pharmacognosy and Phytochemistry. We are seeing quality control methods of herbal drugs, and in that so far what we've reached is till the chemical methods of analysis of drugs. Now if you remember, the chemical methods of evaluation of drugs includes qualitative methods which we have discussed, that includes phytochemical, microchemical, limit test and TLC, as well as if you go to see the quantitative methods, we have methods for determinations of different constituents using simple chemical tests as well as chromatographic techniques. In the previous sessions, we saw one of the chromatographic techniques, that is your HPTLC. In this particular session, we will focus on HPLC as a method of evaluation of herbal drugs. Not only is HPLC used as a chromatographic method for quantification, you will see along with HPTLC this chromatographic methods hereafter have also been used for determination of pesticidal residues, aflatoxins and residual solvents. But when it comes to residual solvents, your gas chromatography would be more preferred, but for determination of pesticidal as well as for aflatoxins, both your HPLC as well as UPLC methods can be used for the quantification as well as for determination. So let us see what is this HPLC and what are the HPLC methods. So HPLC means high pressure liquid chromatography, also called as high performance liquid chromatography. Now it is very much similar to your HPTLC. If you remember, in your HPTLC we had a thin layer of what is called as stationary phase. Now this stationary phase was silica many a times, or it could be alumina, or it could be cellulose. Now imagine this stationary phase, instead of putting it on a plate, if we fill it in a capillary or if we fill it in a tube, what is going to happen is exactly the same phenomenon, but rather than running in a planar manner, it would run in a 3-dimension manner. Not only that, if you take this silica and further reduce the size of the particles, the efficiency or the resolution of the bands or the resolution of the substances, depending upon their polarity, will also enhance. But at the same time, what happens is, as the particle size comes down, what happens is there is more resistance. So your mobile phase will not flow naturally, but it has to be pushed through it. This pushing is what requires pressure, and hence this technique is called as high pressure liquid chromatography. So let's learn about this chromatographic technique. Again, when I have to analyze my herbal drug material, a herbal formulation, polyherbal formulation, or any other formulation, say for example your shampoos, your toothpaste containing all this herbal materials, I will take those and again do a sample preparation. This sample preparation will extract my molecules to be determined from this compounds, and then I will subsequently inject or insert this compound into a chromatographic column. Now how this is done is, you can see here, this takes help of your mobile phase. This is the same mobile phase that was used in TLC, but because I said the particle size is fine now, it requires a pump to push in. So this is what you call it as a solvent delivery pump, and this is actually your plate, but this is your plate in a 3-dimensional form. So it's actually a pipe filled it with your what is called as stationary phase, which could be your silica, or sometimes depending upon if it is a reverse phase, it is octadecyl coated silica and so on. So here, now if you remember, in your TLC we used to spot a sample either manually or with help of applicator. In this case, the sample is actually injected in a pipe. and this injection is done manually, or it could be done with the help of device called as autosampler. Now once inserted in this pipe or once inserted in this mobile phase, it mixes with this mobile phase and starts traveling through the column. Now as it is traveling through the column, what happens is a very same phenomenon that we observed in TLC. As it moves, it goes on resolving. So you can see at the entry point many of the compounds are together, but as it is moving through the column, because of its affinity towards the stationary phase or towards the mobile phase, depending upon its polarity, it is going to partition between your stationary and mobile phase and eventually elute out. So in TLC, we stopped at a point, say about 90% of the plate, and then we measured retention factor. Imagine if we don't stop the plate, what is going to happen? Slowly each of this band is going to run forward. Now we allow in HPLC this bands to move forward so much so that we allow it to run out of column. Okay, so now once it runs out of column, it will come back to the tube. Say for example, this orange is your mixture. It has separated into two components, pink and yellow bands, as you can see. Now this pink and yellow band are traveling through this, and what happens is your yellow band will run into your mobile phase again. Okay, now it has come out of column. Now this will travel with the mobile phase and reach the detector where it is quantified. So it will give you a signal or it will give you a peak based on its UV maxima. Again, because after this there is solvent, again there will be decrease, there will be no UV absorption till your second compounds come in. Then again you will see some UV absorption. So say for example, I have one compound or this pink compound eluting out. So this pink compound elutes out. Now what is this is, it is seen or it can be visually represented by a chromatogram. So this HPLC chromatogram have been taken from the website of Shimadzu. So what is done is the output is seen something like this on your computer on basis the software. So you have something called as time. So how much time is required for this peak to come out and reach the detector. So how do you do this? So this is the point where you actually injected the sample. Remember here. So this is the time where your actual run time, your computer starts calculating. The moment you inject, it's going to sense that you injected and it's going to start counting the time. So this is something called as your injection time, and then you will see that there are certain solvents or certain residues which you use in your preparation of samples. Those do not retain on this column. So those will directly flow. So from your injection, say for example, you prepared your sample in methanol. So this methanol will not be restricted, it will come out. Now even methanol will be detected by the detector slightly. So this is what is called as your solvent peak or often referred to as T0. T0 is the time taken from your injection time till a point your solvent, mostly the solvents which do not retain, come out. After that you will get again a plain baseline because nothing is coming out. Your baseline is basically your mobile phase coming out as it is unchanged. Till then you see your substance coming out. Now depending upon that, if you have a UV detector, this substance is absorbing and slowly you will see the substance coming out and it will be a nice peak. Now this peak will have an intensity depending upon how much it absorbs, depending upon its concentration, as well as you can measure the peak area. So there are two components, there is peak height and there is peak area. Both of them are measured, and then what you do is for quantification purpose, you plot a graph. You plot a graph of peak area here versus concentration in ml. So when you plot this, you might get a linear curve, and based on that you might want to plot your sample and you will get your unknown concentration. So this is in brief or in summary how your HPLC works. So there are a few parameters we need to see in a manner very similar to your HPTLC. The first one is sample preparation. Now the sample preparation for your HPLC also remains almost the similar. So you have to consider the same parameters. What is the concentration of my phytoconstituent in plant? Accordingly, I'll have to extract my raw material. What is the solubility of my phytoconstituent in the extracting solvent? What is the stability? Is it going to be stable? Is it going to be completely extractable or not? If it's not going to be completely extractable, if it has a little less solubility, like I said in the previous session, you could use a Soxhlet extractor to ensure more complete extraction. After that, you should see that other impurities. Now, this other impurities may be very related substance. So, if you see cinchona and I want to check quinine, you could have your quinidine, cinchonin, cinchonidine coming out. So, this related substances or related alkaloids, do they have the same solubility? Is there any way I can get rid of those to selectively quantify only quinine? These are some things. So, if I know my quinine is soluble in one particular solvent in which this other compounds are not, I would prefer such solvent for selectivity. But at the same time, I should ensure that the extraction is complete because my aim is to quantify here. So, one more thing which here differs from your HPTLC is, in this case you are going to run the sample. So, we just saw, if you remember this, we just saw we are going to inject the sample in this. Now, say for example, my mobile phase is water. I am just giving you a random example. My mobile phase is water, but I have extracted my sample in alcohol, and my compound, say for example, or routine, quercetin, are not soluble in water. So, in that case, what happens is, the moment I inject dissolved quercetin in methanol and I inject it to a mobile phase which is just water, it is going to precipitate out, because your injection is just going to be like 5 microliters to 20 microliters, but your mobile phase is in ml quantities. So, this, because of its insolubility, will precipitate out. Worst case, it is very close to the column. So, all this precipitate or particles will go and clog the column. That should not happen, and for that reason, during sample preparation, especially for HPLC, sample before its injection is kind of solubilized in the mobile phase. So, even if my mobile phase is acetonitrile water 90-10, I will take my alcoholic extract, I will first solubilize it, then I will filter it so that nothing remains. Now, here I have to ensure that the complete solubility is there, because if I filter it and all my analyte is staying on top of filter paper, that is not going to be an accurate analysis. So, I need to take into account the solubility, especially the solubility with respect to mobile phase. In some cases, buffers are also added in mobile phases, such as your phosphate buffer, in order to enhance the solubility of the substances. After that, despite that, we still don't want any particles to clog our column, so we use what are called as syringe filters. So, once that is done, you take the extract, pass it through a syringe filter. You can see there is a cartridge, in this there is a filter film or a filter paper like a membrane, and then what comes out is actually a clear filtrate. Now, you do this and that is what is injected here. Okay. So, I will give you one example where your sample preparation is kind of used very nicely, where you saw in your alkaloids. In your alkaloids, we said that the free bases are more soluble in organic solvent, whereas the salts are more soluble in your water. So, if my mobile phase is water, in this case, it is better for me to extract my alkaloids in acid, because this acid will convert alkaloids into alkaloidal salts, and this alkaloidal salts will easily dissolve in my mobile phase. Now, imagine if I basify and then extract my alkaloids will be as free bases. Free bases are water insoluble. The moment I inject it in my HPLC, my alkaloids are going to be precipitated. So, that due care I have to take, and many a times in that case we use what is called as guard column to prevent our analytical column. So, what is this guard column and what is this analytical column? Let us see different columns that are used. Now, there are two types of column principally which are used in HPLC. One is what is called as analytical column, the column which actually resolves the substances into like your bands or different peaks as we saw. And guard columns are kind of preventive columns. We just saw that due to some incompatibilities between the sample and the mobile phase, there are chances that your substance might precipitate. In that case, if you see the particle size of analytical column is very fine. So if you see it just 2.5 to 10 micron. So there's a very high chance that I will clog it. What will happen, as it is I am pumping it with a high pressure. Imagine pumping a column which is already clogged. The pipeline would kind of push it to the extent where the machine will start leaking. So in order to prevent that, what I can do is I can put a guard column which is little bigger in particle size. So if you see here, your guard column has a particle size of about 40 micron. That is like a good filtration media, and that will block most of your particles without clogging your analytical column. So guard column are very tiny, about 2 centimeter in length and just about 4.6 mm internal diameter, but this are kind of saviors when it comes to your herbal extract, especially when you have a polyherbal extract where you don't know what is going to precipitate out when it's going to be mixed with your mobile phase. So guard columns do protect it, and then this is subsequently followed by analytical columns. Analytical columns are the ones which actually resolve your substances. They, depending upon their stationary phase, are classified into different classes. This includes reverse phase column, where your silica is coated with something like your C18 chain or a C8 chain. So that is very lipophilic. Phenyl pentafluorophenyl, this is the column base, or this is a stationary phase which is mostly used for determination of your pesticidal residues. Then you have amino and cyano columns. Amino and cyano columns are generally used for polar compounds. This includes your carbohydrates and water soluble compounds. Your column length would be anywhere, especially the analytical columns, you can see here they are anywhere between 10 centimeters to 25 centimeters, whereas you can see here these are your tiny guard columns. This could be somewhere between 1 to 2 centimeters. Okay. Now most of your phytoconstituents, if you go to see, are or can be detected by your C8 to C18. Majority of the assays, especially if you see the pharmacopoeial methods, are all done by C18 columns. So now going up from stationary phase to mobile phase. What mobile phase do you use in a HPLC? So if I am talking about normal phase, in normal phase my stationary phase, that is my column, is polar. That means my mobile phase has to be non-polar. In that case, your solvents such as hexane, heptane, isopropanol, ethyl acetate, or even tetrahydrofuran. So you will be using more of lipophilic solvent. Whereas if my column is a reverse phase column, that means something like your C18, it's extensively lipophilic. In that case, my mobile phase will be polar. So this includes solvents which are very polar, that is water, methanol, certain times buffers. To enhance the solubility, we can add phosphoric acid, formic acid. Acetonitrile is also used in case if you want to make it more non-polar. So these are the different mobile phases. Now you can have a mobile phase, and HPLC has a slight advantage here is when you did your HPTLC, you had a fixed mobile phase. You could not change it and the whole plate runs like that. In your HPLC, you can change your mobile phase with respect to time. So this, if your mobile phase is fixed, say for example methanol 90, or say for example acetonitrile 90, water 10, and throughout your analysis, if that is the mobile phase running, I call it as isocratic mobile phase. But at the same time, if I want to change it, now this is generally done for a faster elution and more sharper peaks. In that case, what is done is after every minute I will change. So maybe initially I started with acetonitrile water 90-10, but after say for example 1 minute I change it to 80-20. After maybe 5 minutes, I change it to 65-35, and that goes on. So what happens is I'm gradually changing the polarity of my mobile phase. Initially acetonitrile was very high, that means it was little non-polar, but later on the acetonitrile came down to 65 and water increased to 35. So from non-polar I went to a little polar mobile phase. So I can do that, and that helps me achieve a shorter run time and much sharper peaks. So yes, you can use or you can play with your mobile phase to do that also. The pharmacopoeial methods of especially your amla also uses what is called as gradient elution as per the Indian Pharmacopoeia. Now going to the detection. Now these compounds are coming out. How do you detect it? There are different type of detectors. The most simple detectors which were there in your colorimetry, which were there in your HPTLC, as well as which are there in your HPLC, includes your UV vis detectors. So the moment your compound is coming out, there is a particular wavelength which is being measured, same like your UV spectrophotometers, and this is going to measure everything that is coming out with respect to time. So you can see here, say for example, when I inject a cinchona extract, you will see that this is something which is the solvent peak T0, and then what happens is slowly compounds start eluting out. These compounds are from polar to extensively non-polar if it is a C18 column. So then first at 5 minutes your cinchonidin is coming out. So I set my wavelength, say for example at about 223 nanometers. So I see one peak, that's cinchonidin. After some time your cinchonin is coming out. After some time your quinidin is coming out at 7.5 minutes. At 8.3 minutes your quinine is coming out. At 9.7 minutes. So you will see that based on their UV absorbance, you will see your compounds being seen. Now in some cases, it so happens that the compounds that you want to analyze absorb at a different wavelength. Say for example, quinine might absorb at 223 nanometers, but a anthocyanin like a cyanidin may absorb at 500 nanometers. In that case, I can use what is called as photodiode array detector. Photodiode array detector measures all the wavelength. So I can quantify at 500 as well as I can quantify at 200 simultaneously and still estimate both of them. Now there are certain compounds like quinine sulfate which we measured by spectrofluorimetry. This can be measured, or this quinine you can even convert to quinine sulfate and check the fluorescence using the fluorescence detectors. In some cases, when you want to actually detect the compounds, a good technique is to analyze their mass. So this LC is given an hyphenated output to a mass spectrometer, to a mass spectrophotometer, and in that case what you will get is the mass, and that will help you identify each of this peak. In some cases you use what is called as electrochemical detectors which measure the current, and conductivity detectors which measure the conductivity. Now some cases, or in some cases, what you will observe is this UV properties as well as fluorescence properties are not very good of a given substance. So in that case you can just use a simple RI detectors. They are very primitive but still not as sensitive as your current detectors such as your LSD, but they do the work of RI detection and can quantify the compounds even which are not UV absorbing. Then you have your evaporative light scattering detectors, wherein the mobile phase is evaporated and then whatever the residue is left, the light is scattered through that. So you will see that depending upon what the residue is, you will get the light scattering, and it is a more sensitive detector as far as HPLC is concerned. Now let us see some examples. Here is in a method of estimation of digitoxin using the British Pharmacopoeia method, and you can see it's a very simple method which uses a reverse phase column C18, and a mobile phase is what you call it as isocratic. It's not changing. Fixed mobile phase, water acetonitrile 72:28. Because it's a glycoside, so I need a more polar mobile phase with a UV detection at 220 nanometers. So when I inject it, what I'll get is, you can see digitoxin somewhere elutes at your 5.3. So, you can see it in the standard, you can see it in the sample as well. So, I can use that for quantification if I know the area under curve as well as the concentration of the standard. Now, in some cases not only just quantification, it is also like your HPTLC where you can develop a chromatogram. So, if you remember, we just discussed quinine. So, what is here is a typical fingerprint of cinchona. I can use this fingerprint and then I can analyze another species of cinchona, Legeriana, Saxirubra, officinalis, and I can check whether the amount of this alkaloids is same, the area under curve of this is same or is it different. In some cases, even if there are unidentified substances, I can still see the RT of peak and I should say that if it is Cinchona officinalis, that unidentified peak should be seen at this particular retention time. So, it helps me in identification of plants via fingerprint and understanding the species variation. It helps me in quantification, validation and standardization of raw material, because once I quantify, I can easily understand if there is any seasonal, geographical or any variation brought about. Not only that, I can see the foreign peaks which should not be there in my sample, and I can tell if there is adulteration. Again, I know the fingerprint. So, if there is some synthetic drug which is provided to me, say for example, some other lipid which has been a synthetic lipid, the HPLC RT, that is the retention time, will change, synthetic colors because they will absorb at a different wavelength, and other plant materials. Not only that, if you use your fluorescence detector, you can even quantify your aflatoxins. This is a very good method in terms of its sensitivity. It outperforms your HPTLC as well, and hence can be used for detection of even small nanogram or picogram quantities of your analyte in your herbal formulations. Now, we will move on to the next part, and that is determination of pesticides. Now, pesticides is a big issue especially with herbal drugs, because most of the herbal drugs become infested by pests, and in order to prevent it, your farmers often spray it with numerous pesticides. But an important quality criteria when we are manufacturing herbal medicines is this pesticide residue should stay within the limits and should be safe for consumption if it is not possible to completely eliminate it. So, in some cases you will see that limits of certain pesticides have been specified by the pharmacopoeias itself. Say for example, for ethion it is 2 mg per kg, it should not exceed that. For methoxychlor it is still minute, that is 0.05 mg per kg of body weight. Okay. But there are certain substances which are new, we do not know. In that cases your WHO or most of the pharmacopoeias give you a formula of limit of pesticide, which is your acceptable daily intake, that is how much you can consume safely per day in terms of mg per kg. These values are often given by WHO into your body weight. Mostly it is taken as 60 kilos, and this is divided by what is called as daily dose of herbal drug. So, if that is a formulation, how much of that drug you are going to consume per day multiplied by 100. So, this is how you kind of estimate it, but now your pharmacopoeias, majority of them, the limits have been laid down. For newer pesticides, this is the one what you are using. Now, this determination of pesticides, how do I carry out? Now, this determination of pesticide has a very interesting sample preparation methods which have been standardized. It is called as your Ketchers method. Now, Ketchers refers for quick, easy, cheap, effective, rugged but safe method for sample preparation. Now, this has not only been used in pharmaceuticals, this has been used in foods and many other industries where your determination of pesticidal residues is vital. So, Ketchers method, I have just taken it from their site. You kind of take about 10 gram of sample. This could be a fruit, vegetable, this could be a herbal drug raw material, or this could be your formulation. Okay, now to that you add about 10 ml of acetonitrile. Now what happens is when you're taking fresh fruits and vegetable, naturally they have some water in them. So you need not add water. But in cases if your raw material or herbal drug material is dry, your acetonitrile many of the time is not able to kind of soak in properly. So for 10 gram of sample, you first macerate it with 10 ml of water and then subsequently with 10 ml of acetonitrile. But if it is a moist or a wet drug like your vegetables, fruit, in that case direct acetonitrile is also good. In some cases you can add internal standard to check if I have added 1 mg of internal standard, can I quantify that back. So if it is coming as 1 mg even after analysis, that means I have extracted my compound completely. Otherwise, it's a incomplete extraction. So I'll add deliberately an internal standard to check if I'm extracting it properly. Then I will kind of pulverize or grind it, make the sample into fine paste to facilitate extraction. And then what I do is, to that I will go on adding salt. Now you know, as water becomes saturated, water and acetonitrile initially are very nicely miscible, but as water becomes saturated with your salt, especially NaCl and magnesium sulfate, you will see the acetonitrile phase separating out. We want that. So that phase separation happens and it can be fastened by centrifugation. So you can do a centrifugation and take that acetonitrile layer. This acetonitrile layer still contains lot of other impurities including your compounds. So take for example, if you extracted turmeric, it will contain curcuminoids plus pesticides. So in some cases a sample cleanup is recommended. So this sample cleanup is done by a solid phase cartridge, and this solid phase cartridge is the one which is kind of loaded with the help of a mobile phase in your HPLC itself, or sometime it is done separately on a different pump, and then you change the mobile phase to cause unloading. So this solid phase will take up most of your impurities and leave only or leach out only the pesticides. So majority of your cleaning up happens there. In some cases sorbate such as PSA is used, and then eventually what is eluted out is a very clear solution containing pesticides. Now once this pesticide containing solution is ready with you, then I just need to inject it in my HPLC and I need to analyze it. So here are few examples wherein your HPLC has been used for analysis. So this is a column called as Nuchrome BH by Select. Now here what they have done is they have used acetonitrile water, and for creating that little pH gradient they have used H2SO4. So it's a gradient mobile phase. You can see here initially my acetonitrile is 10, water is 90 and sulfuric acid is 0.05. But after 5 minutes I am going to change acetonitrile from 10 to 50, water from 90 to 50 and sulfuric acid from 0.05 to 0.02. When I do this and I just keep it for a hold for another 5 minutes, I can see my most of the pesticides being separate out. So you can see here, this is a list of pesticides, the numbers of which are placed here. So you can see your monocryptophos, you can see your metribuzin, and all of this depending upon their mobile phase will have a slight different elution and slightly different what is called as area under curve. So I can use different mobile phase, optimize it depending upon the nature of pesticide that I want to determine. Not only that, the industries now have started taking into account your machine learning algorithms. So this machine learning algorithms, if I couple my output with a mass spectrophotometer, my machine learning algorithm with a pre-saved library will tell me what exactly the pesticide is. So I need not have my pesticide standards. The library search along with ML algorithms will rightly tell me that this is my drug, this is the content of my actives, and this is the amount of pesticide that it contains. Same method or same technique is also applied for detection of aflatoxins. So yes, HPLC is a very important tool as far as quality control is concerned. It is going to help me out in quantification, detection of adulterants, species identification, standardization of my formulation. Not only that, HPLC also helps me in understanding if there is any aflatoxin present, is there any pesticide present, and nowadays even in the detection of newer analytes. So here are few references if you wish to go through more of this content, and thank you everyone for your patient listening.